Okay, welcome back to Physics 123b, 223b. Last time we looked at DC circuits, that's circuits that don't change voltage over time, and that's nice if we want to light a light bulb or run a motor, not very useful if we want to convey information, which of course is what this course is all about. So we need a way of creating time-dependent circuits, circuits where the voltage changes with time, and to do that we need a time-dependent element. Resistor certainly isn't that, and even the diode, while nonlinear, is still time invariant. So we need a new element, and that element is the capacitor. So let's take a look at our capacitor. Capacitor, physically and schematically, are drawn pretty similarly. Here's what a schematic capacitor looks like. It's two flat plates not connected to each other, and an actual capacitor is exactly that. It's two conductive plates, typically metal, not connected to each other. And in fact, the main difference with a real capacitor is there's usually some material, an insulating material, between the plates called a dielectric. And the purpose of a dielectric is to increase the strength of a electrostatic field. We have two plates. They're conductive. And what happens is, if we apply a current to the capacitor, current flows in, we have electrons piling up on one side and positive charges on the other, and we end up with a capacitor is charged. And if you think about it, because it's a insulator, if we remove the voltage source that supplied the current to charge these plates, there's nowhere for this charge to go, and it just sits there. And it sits there and creates an electrostatic field between the two plates. That's energy. So if we place a voltage across our capacitor, what we find is that the charge, Q, is equal to the voltage times a constant C. And this constant is in units of capacitance. And that capacitance is a function of the geometry of the capacitor. The area of the plates, the distance between them, the dielectric, and it's a constant. It depends on the physical construction. The units of capacitance are farads. We usually abbreviate that F. Now, 1 farad is actually a really huge amount of capacitance, and in this course we'll mostly be using microfarads, nanofarads, and occasionally picofarads. So this is 10 to the minus 6th, 10 to the minus 9th, and 10 to the minus 12th. And typically we're going to be using 100 picofarads to maybe 10 microfarads is a range that you might see in this course. Bigger capacitance means more charge stored for a given voltage, so more stored energy. So a big capacitor can store a lot of energy, and I think we should probably stop here and take a look at a demo of capacitor storing charge. Okay, we're going to demonstrate capacitors storing charge. I have here a supercap. That's a capacitor that's designed primarily as a voltage backup. It's super because it's 5 farads, which is quite a large value. You won't find that in a normal capacitor. I've got it hooked up with a resistor, current limiting resistor, and LED, so we'll know when it has charge. This particular super cap has a maximum of 2.7 volt that can be applied to it, so I have a 2.7 volt supply. What I'm going to do is I'm going to charge up this super cap. The LED will come on, and we'll watch that, we'll see that the LED stays on for a while, showing that we've stored charge. So the first thing I need to do is hook up my 2.7 volt supply, and this is a polarized cap, so I have to make sure I hook it up correctly. That's the positive side. And I'm going to start a timer to time how long it takes to charge. The particular power supply I'm using is current limited to 1 amp, so it will take a while to pump all the charge for a 5 farad capacitor at 1 amp. So I'm going to hook that up, start it, and when I see the charge starting to come down, I'm going to turn off I'm going to capture the time, you notice that we started out at, okay, so the charge has gone down right there, and we're now up about 2.7 volts. We start out when we're pumping charge in at a lower voltage because we can only put in 1 amp at a time, and then gradually we come up to 2.7. So now we're fully charged. We're at 2.7 volts. I'm going to disconnect the power supply, and you'll notice that our LED is still on. I'll turn off the lights so it's sort of easy. And now what I'm going to do is just wait and see how long it takes for the capacitor to discharge. We don't need the power supply anymore, or the multimeter. And let's zoom in on the relevant LED and time, and we'll just watch and see what happens to that LED. I'm not going to make you watch the whole thing. We will skip ahead and see when the LED starts to dim. And here we are after an hour, and there's still some energy left to light up the LED. And of course, since the LED has a forward voltage of about 1.5 volts, that says we're around 1 volt to 1.5 volts left in the capacitor at this point. Okay, so we took a look at this demonstration. We saw that capacitors store charge. Let's take a look at what capacitors look like. We really have two major distinctions in capacitors. There are ones that are polarized. That means that you have to apply positive voltage to one side, negative voltage to the other, and ones that aren't. And the main difference is that large value capacitors typically use a dielectric that has polarity. It's a liquid or a paste, and it breaks down if reverse biased. So here's some examples of some electrolytic capacitors. The first thing to note is the leads on this particular capacitor come out both on one side. This is known as a radial capacitor because the leads come out of the radius. This is an axial capacitor because the leads come out of each axis. There's no difference in them. It's purely a mechanical decision how you're going to mount the thing. These are all electrolytic capacitors. One thing that's very different between capacitors and resistors is because capacitors depend on physical size, larger value capacitors or higher voltage capacitors typically are larger in value. The relevant parameters that we care about in addition to capacitance are voltage. There's a maximum voltage, and if we exceed that, we break down the dielectric and the capacitor fails. And of course tolerance, which is exactly the same as resistors, except that capacitors tend to have looser tolerances. We typically use plus minus 5% resistors. A plus minus 5% capacitor would be unusual and expensive. Our capacitors are typically plus minus 10, plus minus 20. And for something like an electrolytic capacitor, you can often find minus 10, plus 50, because typically they're used in applications where you don't care about them being too big. Now these are pretty easy to read. Let's zoom in here. Well, we know that that's a 220 microfarad, 35 volt capacitor, so you can't put more than 35 volts across it. And this minus sign tells us that this lead should always be more negative than that. What that means is you cannot use this in an application unless you can guarantee that the lead over here will be more positive than the lead over here. So that's one of the limits of electrolytic capacitors. And in our lab, any capacitor over 1 microfarad is typically polarized in electrolytic. 1 microfarad and below are non-polarized, and they use a different technology. Another capacitor here. Once again, a maximum of 16 volts, 220 microfarads, and this end, the end that the negative arrow is pointing to, always has to be more negative. And then finally, this is a capacitor, a type called tantalum. I don't know that we're going, well, you can barely read it. It's 4R7UF. That means 4.7 microfarads. and it says 50 volts. This is another electrolytic capacitor. This is a smaller value. Once again, there's an arrow pointing to the negative side, and I don't know that we're going to be able to read it, but it's plainly marked. Well, it's plainly marked if we had better eyes with its value right on the side. Now, let's take a look at some other capacitors. These are all non-electrolytic. This is a, let me turn off capacitor. You can at least see that it's 12 volts. Another capacitor is another type of ceramic capacitor. Another type of ceramic capacitor. These are all different types of capacitors. Reading them is much more difficult. The one here is fairly easy to read because it just has values written on it. A little hard for us to see. The rest of them use a various type of code. I'm not quite sure I can see it. Let's take a look. So this one, I don't know, you probably can't see it, but it says 154 on it. The 15 is multiplied by 10 to the fourth to get the number of picofarads. And it's 0.15 microfarads, 150 nanofarads. If you don't want to learn the code, your multimeter has a range that will read capacitance, and I would suggest you use that when necessary. In this course, we're not going to be using capacitors a whole lot because in the digital world you don't use them, and in most circuits. And where we do use them, we're not going to care a lot about the values. So you're not going to have to worry about it other than one or two experiments. But these are all different value capacitors. Now let's think about what we can use a capacitor for. As we saw before, we saw that the charge was directly proportional to the capacitance, constant, and the voltage. But of course, we don't care about charge. What we care about is charge moving, which is current. And how do we find out what the current is? Well, if we take the derivative of both sides of this equation with respect to time, we get dq dt is equal to dcv dt. But since c is a constant, this is equal to c dv dt. And dq dt is just current. So that gives us the classic equation for a capacitor in the time domain, I equals c dv dt. So what does that tell us? Well, there's a couple important things. If I equals 0, the voltage across the capacitor is not changing. So if I charge up a capacitor to some voltage and remove the voltage source and the capacitor is no longer connected to anything, well then the voltage across the capacitor will stay the same. Now that's true of an ideal capacitor. Real capacitors have some losses, and if you leave them long enough they'll self-discharge. But for the most part, capacitor will hold its voltage. If I does not equal 0, the voltage across the capacitor is changing. And that's important. So that pretty much describes our capacitor. We're going to look at our capacitor later in a different way. We're going to look at it as a frequency model, and we're only going to look at that very, very briefly for this course. But for the most part, this rule, I equals c dv dt, allows us to figure out what we can do with capacitors. So let's take a look at a particular experiment. Let's take a capacitor. Oh, let's make it 1 microfarad because that's a nice even number. We're going to look at the voltage across the capacitor. Of course, when I write V out here, that voltage has to be referenced to something. It's referenced to ground, but I've connected the other end of the capacitor to ground. And I'm going to use a switch to select between two current sources. This current source is a 1 milliamp current source going down, And I'm going to have a 1 milliamp current source going down in the other direction. So I can either have current flowing into this capacitor, 1 milliamp, or if I move the switch from position 1 to position 2, I can have 1 milliamp and that would flow out of the capacitor. V out, we're measuring with a perfect multimeter, so no current flows out V out. So any current that flows in this circuit has to flow either into the capacitor or out of the capacitor. And what I want to do is I want to graph V out over time. And the other thing I'm going to do down here is the switch position. And let's assume that at time t equals 0, the capacitor voltage is 0. Now, why do I have to do that? Well, remember, I said that if you charge up a capacitor and disconnect it from any voltage source, it retains its current value. That means that if I say to you, what is the voltage I would measure across that capacitor if I took my multimeter? What's your answer? Well, the answer is any voltage between 0 and 35 volts. How do I know that? Well, I can't apply a negative voltage to this capacitor. Electrolytics don't work negative. And I shouldn't apply more than 35 because it's not guaranteed to work. But if I were to apply any other voltage and remove the leads and then show you this capacitor the way I did, there would be no way to know what value this has. So I have to always specify an initial condition. I'm going to specify an initial condition here. And I'm going to move the switch to position 1 at time t equals 0. So in this period, I'm in position 1. I have 1 milliamp flowing. Where does that current go? Well, we know by KCL that that current has to go somewhere when it hits a node. This is a node. It can't go this way, has to go this way. So it's going to flow into this capacitor. And what do we expect? How do we expect the capacitor voltage to change or not? Well, I sub C is constant. It's 1 milliamp. C is constant. That means dV dt is constant. And since current is flowing into this capacitor, this side of the capacitor has to be getting more positive than that side. If dV dt is constant, it means dV dt goes up linearly. So I need to add a third position because I want to be able to turn off charge going in and out of the capacitor. So at time t equals t1, I'm going to move the capacitor to position 3. When I move the capacitor to position 3, it is not connected to either current source, and in fact, it's not connected to anything. So the question is, between time t equals t1 and t equals t2, what is the capacitor voltage? Well, I equals c dV dt. I is a constant, but it's 0 now. C is a constant, but dV dt has to be 0 or else I couldn't be 0. So that means that there can be no change in the capacitor voltage during period t1 to t2. And then finally, I'm going to move the switch to position 2 at time t2. So I'm going to move the switch down to here. 1 milliamp flows out of this node. That means 1 milliamp flows out of this node, which means current and charge gets pulled off the capacitor through the 1 milliamp current. This voltage has to decrease. How does that voltage decrease? Well, I is constant, C is constant, dV dt is constant, and in fact, I is the opposite of what it was in position 1 because their current was flowing into the capacitor, 1 milliamp. Here, 1 milliamp is flowing out. So we'd expect this to go down linearly, and in fact, it will go down linearly with the same slope, the negative of the slope that we had charging. Okay. Let's get ourselves a different color. We know that 1 milliamp equals 1 microfarad times dV dt. Excuse me, dV dt. We've got 1 milliamp divided by 1 microfarad. Well, that's 10 to the third minus third. That's 10 to the minus sixth. So 1 EE minus 3, 1 EE minus 6 divide, and that's 1,000 volts per second. So the slope of this is 1,000 volts per second, and then the slope of this has to be minus 1,000 volts per second. And in fact, this is a technique used to create things like triangle waves in a function generator. Current sources are somewhat expensive, somewhat rare. We're not going to be able to use a current source. So let's think about what we could do if we didn't have a current source. Well, we have resistors. Resistors control current. So let's try a slightly different circuit. Oh, let's do 10 volts. All right, so here we have an RC circuit, typically called an RC circuit, a resistor and a capacitor. We start out with the switch in position 2, and we're going to do the same thing we did before. We're going to graph time versus V out. 10 volts is up here, 0 volts is down here. T equals 0 is here. And before t equals 0, we're going to have the switch in position 2, and then we're going to move it to position 1. So position 2, KVL, tells us that there's 0 volts out. Why? Well, from here to here is 0 volts. This switch is a short circuit. And since the voltages around the loop have to add up to 0, the voltage across the capacitor has to be 0. At time t equals 0, we move the switch to position 1. Let's think about, let's make R equal to 10 kiloohms, because it allows us to think about how much current flows. When I move the switch to position 1, what's the voltage across the capacitor at that instant? Well, at that instant, it hasn't changed. We move our switch from 2 to 1. We know that the voltage across the capacitor can't change instantly. Why is that true? Well, I equals C dV dt. If we had an instantaneous change, which is to say a change in voltage of the capacitor over 0 time, capacitance is a fixed value. The only way to get this voltage to change in 0 time, that by the way is an infinite slope, would be for the current to be infinite, and we just don't have a lot of sources of infinite current around. So what that says is we switch the capacitor up to here. It's 0 volts at that time. That means there's 10 volts across the resistor, because by KVL, the voltage across the resistor plus the voltage across the capacitor has to equal 10 volts. That means we've got 1 milliamp flowing through this resistor. Where does that current go? That current has to flow into the capacitor. Okay, if current is flowing into the capacitor, we know that dV dt is changing. And in fact, we're going to start charging linearly 1 milliamp flowing in there, just as we did up here. However, the instant that this voltage, which is the voltage across the capacitor, is bigger than 0, the voltage across the resistor is less than 10 because of KVL. Well, if the voltage across the resistor is less than 10, we have less than 10 milliamps flowing, and the capacitor is going to charge a little slower. Of course, the capacitor voltage keeps increasing, which means the resistor voltage keeps decreasing. And what happens is we have a continually decreasing current flowing into the capacitor, which means that the change in voltage of the capacitor is continuously decreasing, and it asymptotically approaches 10 volts. Why 10 volts? Because once the output voltage of the capacitor, the voltage across the capacitor is 10 volts, the voltage across the resistor is 0. The voltage across the resistor is 0, no current flows through it. If no current flows through the resistor, no current flows into the capacitor, and we end up at 10 volts. That's going to be the terminal voltage. This is a classic exponential curve, and I'm not going to show you the equations, but V out is equal to the terminal voltage times 1 minus E to minus T over RC. Let's see if that makes sense. At t equals 0, let's see, e to the 0, well, that's 1. 1 minus 1 is 0, times 10 is 0, so we'd expect to have 0 volts here. At some very high value of time, well, this would be e to the minus big value, which is effectively 0, so we'd expect to get 10 times 1 minus 0, or 10 volts. So at least this seems to have the right structure. And you'll just have to take my word, unless you're interested and want to have a private conference with me, of where this equation comes from. So this is known as exponential RC charging. The exponent is here. It's not like it gets exponentially bigger. It actually gets exponentially closer to a final value. And this value, RC, is called the time constant, tau. We represent it by tau. So sometimes you'll see this equation minus 1 over tau. Tau is just RC. Okay, and if you actually plug values into this equation for RC, 2RC, 3RC, 4RC, 5RC, what you will find out is that at 1 tau, we are 63% of the way to the final value, which in this case would be 6.3 volts. So 1 RC, we're at 63% the way to the final value. By the way, I put it that way because we started 0 and we were going to 10, so we could just say 63% of the way to 10 volts, but there's no reason we have to start at 0. We could have started at something else. So if we had started at minus 10, we would have been 63% of the way to 20 volts minus 10 volts because we'd started at 10. At 3RC, we're at 95% of the way. And at 5RC, we're at 99.5% of the way. Now, I will usually just call this 99%. I'm not going to worry about the 0.5%. But when you do problems, you can either use 99%, you can use 99.5%. I'm not too fussy. So out here at 5 tau, we're going to be at 9.9 volts. So our capacitor charges to a final value. After 5RC, we essentially assume it's fully charged. And we can discharge it, we can change the voltage, but that's classic RC charging. In almost all the circuits you will see charge capacitors from resistors and not from current sources. Okay, why don't we take a break here and take a look at a demo of charging capacitors with current sources and with resistors and see if any of this actually happens when we have a real-life situation. Okay, we're going to take a look at capacitors. We have our test set up here. We have a power supply set for 10 volts. We have our oscilloscope. Our oscilloscope is set to trigger just once because the phenomenon we're going to look at, which is the charging of a capacitor, starts when we release a button and then ends when the capacitor is fully charged, and it's only going to happen each time we press the button. So we're using the single sweep, single trigger mode of the oscilloscope. And finally, we have our test setup. So what we have is we have a current source. These are special diodes that allow a constant current through. Each one is 0.75 milliamps. We have two of them, so we have a 1.5 milliamp current source. And we have a capacitor. The capacitor is connected to the current source and ground. We also have a push button. That push button is connected between the capacitor and ground. It's in parallel with the capacitor. So our experimental test setup looks like this. When we press the button, the capacitor voltage is pulled down to ground. When we release it, the capacitor is charged by the 1.5 milliamp current source. So let's see what happens when we press and release the button. So I have the button pressed, and when I release it, the capacitor charges. And if you look, what happens is I've released the button right at this point. Before that, the voltage is 0 because I've got the capacitor shorted by the button. A constant current flows into the capacitor, and as we'd expect from I equals C dV dt, here C is obviously a constant, I is a constant, 1.5 milliamps. That means dV dt has to be a constant, and we see that up until right around here. Now what's going on there? Does everything I've told you wrong at high voltages? No, our problem here is our current source requires a certain voltage to be across it. If we go back to our diagram, you'll notice that 10 volts goes between the current source and ground and the capacitor. So whatever voltage is across the capacitor is subtracted from 10 volts, and that's the voltage across the current source. Our current source, even though it pretends to be a perfect current source, it's actually a real current source, and this particular current source needs a couple volts across it to work properly. And what's happening is, as the voltage across the capacitor increases, the voltage at the current source is decreasing, and at some point, the current source just stops acting as a constant current source, and obviously once we get to 10 volts, there's no way the current source could continue to pump current into the capacitor, because if it did, it would imply that the current source can create current out of nowhere. And indeed, we need at least, looks to me, we need about a volt or so across that particular current source. That particular current source is made out of a kind of transistor that needs a volt or so for it to work. So this shows us that I equals C dV dt. Now, here's a question. What's the value of the capacitor? Well, I equals C dV dt. That means that C is equal to dt times I over dV. Well, to figure that out, we know that I equals 1.5 milliamps, and we have to go back to our oscilloscope to figure out what dV dt is. Okay, so we start at 0 volts at time t equals 0. Our time scale is 20 milliseconds per division, so that's 20, 40, 60 milliseconds, and we're pretty linear in this range, so let's just use the first three time divisions. And we can see we go from 0, 2 volts per division, 2, 4, 6 volts. So we go 6 volts in 60 milliseconds. So let's plug that into our formula. So dt is 60 milliseconds, dV is 6 volts, I equals 1.5 milliamps, that should equal C. Let's get out our calculator. All right, so let's see, we've got 60 milliseconds times 1.5 milliamps divided by 6 volts. And that's 15 times 10 to the minus 6 farads, or 15 microfarads. Let's see if that's correct. The blue capacitor was the one that was being charged by constant current. If we take it out and look at it under a magnifying glass, we see that it is 15 microfarads. Okay, so now we're going to try an RC. Current sources are hard to come by, but resistors are cheap. So let's see what happens when we replace the current source with the resistor. Here's our experimental setup. We have our resistor, a 10K plus minus 5% resistor, charging our 15 microfarad electrolytic capacitor. This is unusual, high precision plus minus 5% capacitor. And we have a push button switch which allows us to discharge the capacitor to 0. When we release the push button, current flows through the resistor from the 10 volt rail into the capacitor, and the capacitor voltage charges exponentially. And let's see what happens with this setup. Okay, I'm going to release the button. Now, the first thing you should notice is we're no longer on a 20 millisecond scale. We're on a 100 millisecond scale. This is a much longer period of time. And what we see is when I release the button, we start up something that could almost be linear, but very quickly we start slowing down. And of course, that's what we'd expect. As the voltage across the capacitor increases, the voltage across the resistor decreases. And as the voltage across the resistor decreases, less current flows through the resistor. So there's less current to charge the capacitor. I equals C dV dt. If I goes down, dV dt goes down. We get the classic exponential charging curve. We end up at approximately 10 volts. But it takes quite a while. Let's go ahead and position this so it's easy to see how long it takes. So it looks like we're up at 10 volts, maybe out here, which is 1, 2, 3, 4, 5, 6, say 7 divisions, somewhere around 700 milliseconds. Now we can compare that to the current source. Let me try and release both buttons at the same time. Now let's go ahead and take a look and see what we'd expect. Now we've got a 10K resistor and a 15 microfarad capacitor. 10 to the third times 15 times 10 to the minus 6. That says tau is equal to 150 milliseconds. We'd expect to be about 63% of the way to the final value in 150 milliseconds. So let's go ahead and measure that. Let's see if we can't set our starting point right where we release the button. And we're going to take a look at 150 milliseconds. Let's look at where we're at 6.3 volts. So that's 6.32 volt change in 163 milliseconds. And the difference from the calculated value is probably a combination of component tolerance and measurement error. After 5 time constants, which is 750 milliseconds, we would be almost right at our final value. There's 750. We'd expect to be about 99% of the way, and you can see that after 750 milliseconds, we're at 9.92 volts. We can also check 3 time constants. That would be 450 milliseconds. Right there, we're at 9.4 volts, which is 95% of the way. We're actually at 95% of the way, right around 464. We know that this capacitor is a little bigger than 15 microfarads because it was a little more than 150 milliseconds to the 6.3 volt range. So there's a comparison of RC charging versus constant current charging. Okay, hopefully you're convinced that capacitors actually work. And capacitors are pretty good. Resistors are our best circuit element in terms of being very, very close to the model. Capacitors aren't bad. Some of the errors in capacitors typically are that they don't hold charge forever. There is some leakage. They have some resistance, so when you apply current to them, you lose a little bit of charge. A perfect capacitor is a perfect circuit element. It neither consumes energy, it merely stores it. So you put energy in, you get exactly the same amount of energy back. But in a real capacitor, a little bit of energy is lost. So let's take a look at an application of a capacitor. Here's a capacitor and a resistor. we're going to apply an input signal to this capacitor. And we're going to apply a pulse. And this is the time period of our pulse. And I'm going to tell you that RC is much, much less than the time period of our pulse. Okay? So this pulse goes from 0 to 5 volts. What we're going to do is we're going to think about V out with a fraction of time. Here is t equals 0, t equals p, t sub p. And I'm going to always tell you something about capacitive circuits. I'm going to say something like, well, this has been sitting for a long time. If I tell you it's been sitting for a long time with an input of 0, what would you expect the output voltage to be? So I have to tell you some initial condition. I'm going to tell you that it's been sitting, the input has been sitting at 0 volts for a long time. If you know that, well then, if there's a voltage here, say it's a positive voltage, then current's going to flow through this resistor, discharging the capacitor towards 0. When the capacitor gets to 0, there's no voltage across this resistor, no current flows in and out of the capacitor, it stays at 0 volts. If this voltage were negative, current would flow into the capacitor through the resistor. Once again, as that voltage got more and more positive and closer to 0, the voltage across the resistor would go closer and closer to 0. No current would flow in or out of the capacitor, and V out would stay at 0. So we know that at time t less than 0, the voltage is going to be 0. Now, at t equals 0, this voltage jumps to 5 volts. Well, if this voltage jumps to 5 volts, what happens to this voltage? Well, we said before that the voltage across a capacitor cannot change instantly. So if this voltage is at 0 and this voltage is at 0 before t equals 0, this voltage jumps up at time t equals 0 to 5 volts. The only way to maintain 0 volts across the capacitor is for this voltage to jump up to 5 volts too. The voltage across the capacitor cannot change instantly. It's 0 volts here, it has to be 0 volts here. So at this point, the voltage at V out has to change to plus 5 volts. That seems counterintuitive, and students often find it confusing, but remember, the voltage across the capacitor can't change. Well, what happens once this voltage jumps and this voltage jumps? Well, this is at 5 volts. Current flows through this resistor, so current flows out of the capacitor, so the voltage at the output of the capacitor drops. How quickly does that happen? Well, we know that in 5 tau, the voltage at this point will be back down to 0. And we also know that RC is much, much less than this period, so we expect this voltage to exponentially come back down to 0. All right, so now we're at time t equals p. At time t equals p, V in is 5 volts, but V out is 0 volts. So we're sitting there like this. At times t equals t sub p, the voltage here jumps back down to 0. What happens to the voltage at the output? Well, remember, the voltage across the capacitor cannot change instantly. This voltage has 5 volts across it. 5 volts on the left side, 0 volts on the right side. If the left side drops down to 0, the only way to maintain 5 volts across it is for the right side to drop down to minus 5. And indeed, that's exactly what happens. Again, that may not be intuitive, but the voltage across the capacitor can't change instantly. And since we know that RC is pretty short compared to our timeline here, the voltage drops back fairly quickly to 0 volts. Now, here's a question. What does this waveform look like compared to this waveform? Hopefully, it looks a bit like a derivative. Not perfect, because this should be a perfect spike for the slope of the rising edge and a perfect spike down for the falling edge. But if we make RC small enough, the amount of time this goes up and comes back down will be pretty small. It will look like a derivative. And in fact, this is called an RC differentiator. And why is it a differentiator? Well, V out is equal to I sub C times R, whatever current is flowing out. But we also know that I sub C is equal to C dV dt. dV, that's V in minus V out dt. If we keep V out small, this is, I sub C is approximately equal to C dV in dt, and that we know that V out is equal to I sub C R, which is going to be approximately equal to R times C dV in dt. So V out is going to be essentially the derivative of V in times a constant if V out is much, much less than V in. And actually what that's saying is that the RC time constant has to be small compared to the time we're looking at. Okay, it's not a great differentiator because we have these restrictions. We have to assume that V out is small. We have to keep RC relatively small compared to our input. Why do we have to keep RC small? Well, because V out is proportional to RC, and we need to keep V out small. So the keeping RC small is not a different restriction than keeping V out small. The way we keep V out small is we keep RC small. Okay, and in lab today you'll build this and test it, at least in simulation. Okay, so let's swap the resistor and the capacitor from the last circuit. And let's feed this circuit with an input that's plus 5 volts, minus 5 volts, and has a 50% duty cycle. Now, 50% duty cycle, means that it's high at 5 volts and low at minus 5 volts for exactly the same time. So this is our V in. And let's think about what V out would be. And we're going to assume that V out is much, much less than V in, just like we did last time. Well, we know that the current flowing into the capacitor when V in is positive makes V out go positive, goes higher, dV dt is positive. And when V in is negative, current will flow out and dV dt will be negative. If we assume V out's very small compared to V in, then the current that flows through here is essentially V in over R, because it's V in minus V out over R. And if V out is small, much, much smaller than V in, most of the time the current will be VI over R, and plus minus a little bit. Well, a constant current flowing in or out of a capacitor causes the capacitor to charge linearly. So, let's get ourselves a different color. When this is positive, we'd expect the voltage to be going up linearly, and when this is negative, we'd expect the voltage to be going down linearly. And if this voltage and time is exactly equal to this voltage and time except for the sign of the voltage, we would go up by some amount, we go down by exactly the same amount. And we'd expect something like that as an output. Well, what does this look like? Well, it looks like the integral of that. And in fact, this is called an RC integrator. And as long as we make R and C big enough, V out will change very little. And it will be essentially linear for a constant input voltage. So one question is, why did I draw the output as a slight DC offset rather than having 0 volts as its average DC? Well, this capacitor has been running since the beginning of time with a square wave into it. But at the beginning of time, we don't know whether it had 0 volts across it. Remember, a capacitor can start with any voltage. In this case, this capacitor started with some DC voltage, and that DC voltage won't change because the amount of charge that's pumped into it when we go up is exactly the same amount of charge that's sucked out of it when we go down. And the average is always 0. The average change in DC value is always 0, so the capacitor will have whatever voltage it started out at. It could be 0, and oftentimes it will be. But in this particular time, if we assume this has been starting since the beginning of time, we had some DC voltage on the capacitor when we started. Okay, let's see why this is an integrator. Well, we know that I sub C equals C dV sub C dt, but the voltage across the capacitor here is V out, so this is C dV out dt. I sub C is equal to V in minus V out over R, but we're saying that V out is much, much smaller than V in, and in fact can be ignored. So we're just going to ignore it, and we get I equals V in over R, so we can substitute that here. V in over R is equal to C dV out over dt, and we're going to integrate both sides. Notice I don't have to put the c inside the integral because it's a fixed value. And in fact, I end up with the integral of vi dt is equal to rc times v out, because the integral of dv out dt is v out. And collecting terms, I end up with v out is equal to 1 over rc integral v in dt. And that's our integrator. And notice that as long as we keep rc big, v out is small, and we don't get a lot of error because of the actual exponential nature of the charge. And again, you're going to build this circuit in lab today, at least virtually, and see how it works. Okay, so that's resistors and capacitors in the time domain. There's one more thing I want to do in terms of how we look at capacitors, and that is oftentimes what we want to do is we're going to apply a sine wave, which is a single frequency voltage alternating current to a circuit that has a capacitor in it. And we want to know what it's going to do. Let's take a look at this circuit. This circuit should be kind of familiar, being as it's the integrator we just looked at. But we're applying a single sine wave to it. And this actually is a useful analysis because it turns out we can take any waveform, even the square wave we looked at, and turn it into a series of sine waves. How do we figure out what this does at frequency f? Well, it turns out that another way to look at capacitors is we can look at them as frequency dependent. I don't want to say resistors because they don't have resistance, but frequency dependent elements. And it turns out that the impedance is like resistance, except that it has a frequency. So Z is a function of frequency. And the magnitude of the impedance of a capacitor is equal to 1 over 2 pi fc. So what that says, if you think about it, is that at a frequency of 0, at DC, the impedance of a capacitor is infinite. This is a constant, but f is not. If f is 0, the impedance of a capacitor is constant. If you put a DC voltage across it, no current will flow. That certainly sounds good, since we know that a capacitor has an insulator between the plates. But it also tells you that at very high frequency, at f equals infinity, this looks like a short circuit. Now that's a little bit of a misnomer. We don't have current actually flowing through the capacitor, but the electrostatic field on one side causes current to flow on the other side. So if we add positive charge on one side of the capacitor, negative charge is pulled into the capacitor from the other side. What I want you to pay attention to is that at a very high frequency, this voltage is going to be very close to zero because this is going to have an impedance of zero. You're going to have a resistor here. You're going to have an impedance here. We're going to call that Z sub C. And if Z sub C is zero, well, you have a voltage divider, R and zero, the output is zero. Also notice that at DC, this impedance is infinite, so V out equals V in. That's going to be very helpful on one of the lab exercises. And we're not going to do much more worrying about the frequency response of capacitors, but the thing I want you to remember is that at high frequency, the capacitor is a short circuit, and at low frequency, it's an open circuit. And so if it's teamed with another element like a resistor, it creates a frequency-dependent voltage divider. Okay, so now we have an element that's time-dependent, the capacitor. We aren't going to be using capacitors a great deal in this course. We're going to use them for one very important application, which I will talk about next time, called decoupling. We'll be using them in one or two experiments where we're building circuits that we're using to feed information to our digital circuits. But for the most part, the most important things to remember about capacitors are they cannot change voltage across them instantly. The voltage across a capacitor cannot change instantly because that would require infinite current, which we don't have available. If current is flowing into a capacitor, its voltage is changing. If current is not flowing into a capacitor, its voltage is fixed. And similarly, if the voltage across a capacitor is not changing, no current is flowing into or out of it. Okay, we're done for today. You're going to get together in lab on Tuesday, and we're going to try some circuits using capacitors. Once again, we're going to be using the multi-sim circuit simulator because I'm not sure you'll actually have your hardware yet. And then on Thursday, we'll start playing with real hardware. I'll see you in lab Tuesday, 1:30 my time.